talks today are intended to be kind of introduction, starting from more or less zero, to this homotopy theory of algebraic varieties. I'll do everything in kind of, by far not the most possible generality. I'll restrict myself to varieties over fields, and in fact to varieties over fields of characteristic 0, so that I don't have to say I need resolution of singularities here and I need resolution of singularities there. So, but that's the only reason. So I'll try to simplify the whole thing as much as possible, giving precise definitions everywhere, and of course giving almost no proofs. Okay, here we go. So we start with a field K, which I, as I said, assume to be of characteristic 0 for the resolution of singularities purposes. I'll be considering starting with the category denoted QP of quasi-projective varieties over K, quasi-projective algebraic varieties over K. And what we want to do is to develop some basic homotopy theory in this category based on the notion of homotopy as being kind of a family of morphisms connected through the affine line. So let's give the most basic definition. I'm going to consider just quasi-projective. What is the difference? No, there are no schemes. I mean, they definitely can be reducible. This is important. So let's start with a very basic definition. An elementary A1 homotopy between two morphisms, F and G, from variety X to variety Y, is a morphism H from the product of X with affine line to Y such that H restricted to X times 0 is F, and H restricted to X times 1 is G. This is absolutely the most fundamental definition of the whole theory. Based on it, we want to build the whole homotopy theory. So the first step is to replace the category of quasi-projective varieties by something more suitable for homotopy theory. So the category of quasi-projective varieties itself is very inconvenient. The reason it's inconvenient is that almost no colimits exist there. So the typical problem of, say, defining smash product for two-pointed varieties is unsolvable. For example, I take something like affine line pointed, say, by 0. And I want to define the smash product of affine line with itself. So what I have to do, homotopy theory says, I have to take the ordinary product, and then take there the union of affine line times 0 with 0 times affine line, and contract this union to the point. So take the plane and contract the coordinate cross to the point. This problem is unsolvable in the category of algebraic varieties. So the corresponding push forward just simply doesn't exist. And this is the key technical abstraction to developing homotopy theory directly in the category of quasi-projective varieties. So instead of working with quasi-projective varieties, one starts working with a bigger category, which for the purposes of my lectures, I'll call the category of spaces over K. It's actually invented by Fabien Morel, but this is a different category of spaces from the one which he considered. So we'll have this category of spaces, and we'll have a functor from quasi-projective varieties into this category of spaces, which for now I just denote by I. As soon as I'm done listing the properties of this functor, this I will disappear forever. So for those who know, I can define this category of spaces, but it's completely irrelevant, because what's important are the properties of this category and the functor. So by definition, my category of spaces is going to be the category of sheaves of sets in the CDH topology on the category of quasi-projective varieties over K. I'm not going to talk about it, because it will take too much time. So if one wants to look what is CDH topology, we can discuss it later, okay? I just want, it's completely irrelevant. I'm going to list a list of properties of this functor. No, I'm not going to do that. In fact, I'm going just to erase this thing completely. And say that there exists a functor from Q to K. There exists a category called the category of spaces over K, and the functor from the category of quasi-projective varieties to the category of spaces over K with the following properties. So the first most important property for us about this category of spaces is, as topologists say, it's a complete and co-complete category. So it's a category which has all small limits and co-limits. That's most of what I'm going to say about the category of spaces. Now this functor I commutes with all limits. So recall that limits are gadgets like fiber products. Well, basically, that means it commutes with fiber products. Now, it doesn't, in general, commute with co-limits, because co-limits, when they exist in the category of quasi-projective varieties, are usually very ugly. But it does commute with some special kind of co-limits, which is expressed in the fact that it takes two special types of push-forward squares into push-forward squares. These two types look as follows. Let's consider a square the following form. Where I is open embedding, P is a talmorphism, so unramified covering. No. Right. It's thank you. Right. It's just a talmorphism, not covering. And the additional condition is that if I look at right. Thank you. That this map is an isomorphism. I don't hear, sorry. No. Oh, okay, yeah, this is a reduced closed subscheme corresponding to the complement, right? So for any square like this, no. It's co-Cartesian, so it's a push-forward square. Intravenous. I is this functor going from quasi-projective schemes to spaces. Yes, I'm sorry about this. And yeah, actually, J is much better in any case. Right. So this is one class. Push forward, it means that co-Cartesian, what is the word? What is the other way of saying it? It means that this gadget is the co-limit of this diagram. It means a morphism from here is the same as a pair of morphisms coinciding in here. The second type of co-limits which is being preserved by functor I looks as follows. Let's look at, so again, for any square of the following form, now unfortunately this is going to be I, this is J. There is a reason. So I now is a closed embedding. P is a proper morphism. And the third condition is the same. P minus 1 of x minus z to x minus z is an isomorphism. So, okay, let's go on with properties and then talk more about it. Now let me write this property. There was a question about whether or not it's important that the scheme is reduced. So one of the properties of this functor I is that it completely destroys all the nilpotents. Fifth thing is that, so one can ask how much. So we already see that I is not a full embedding. It does destroy some information, so one can ask how much information does it destroy. So the answer is that, well, the partial answer is that I is a full embedding on the subcategory of semi-normal let me call them varieties still. So semi-normal, I'm not going to explain what it means, but it includes in particular on normal, and again in particular on smooth. So on smooth varieties, it's a full embedding. On normal, it's also a full embedding, and in fact, it's a full embedding on semi-normal, but this I don't want to define. Yes, it's perfectly semi-normal, yeah. So, well, semi-normal means reduced and doesn't have any cusps. That's what it means. That's precisely what this functor destroys. It destroys all the nilpotents and it destroys all the cusps. So it completely disregards it, which is natural because kind of it only remembers topology in some sense, and cusps are non-existent topologically. Finally, so this shows that this functor is almost a full embedding. Now the next property shows that this functor is almost, in a weaker sense, surjective on isomorphism classes. And the property looks as follows. Any space, I'll say space meaning the object of the category of spaces, over K is a co-limit of a diagram of spaces of the form IX. So the only new objects which appear are co-limits of the old objects. So in some sense, this category is obtained from the category of quasi-projective varieties by formally adding co-limits in a nice way. In the diagram, they also can be taken from quasi-projectives. One can actually say, knowing resolution of singularities, one can say that any object can be obtained as a co-limit of a diagram of smooth varieties, and then one gets that all the morphisms come from here. Not at this point. When I'll formulate slightly different statement, which will say that any object is weakly equivalent. And in this point, I'll be able to say that any object is actually weakly equivalent to a just filtered co-limit of objects coming from varieties, but not isomorphic as a space.
When you resolve the singularity, what happens to the R?
Well, so far I wasn't using resolution of singularities at all.
I'm saying supposedly you have the data set 2 varieties going on.
Well, of course, because of this second type of cofibrin squares, if I resolve singularities, then it's just what it's supposed to be. So the contraction actually becomes, in this category of spaces, the contraction in the ordinary sense of a co-limit, of push forward. So let me mention the last property. It follows from all the rest of them. Any object of the form I of x is compact. Compact means the following. That morphisms from I of x to a filtered co-limit of some spaces is the same as the filtered co-limit of morphisms. That's important for homotopy theory, but no. Well, filtered co-limit. Yeah. Now let me mention the reason I didn't want at all to talk about the CDH topology or the sheaves or whatever is the following. I believe, I never tried to prove it because I don't see why it would be necessary, but I believe that these conditions here determine this category uniquely up to an equivalence. So one doesn't really need to know how one constructs it. Just here is everything one can possibly want to know about this construction is written on the blackboard. Well, I use all the properties which are, which I use a lot of properties of algebraic varieties, which are kind of moved to this category through the properties listed on the blackboard. But kind of all one wants to know about the relation between the two is here. Okay, starting from this point on, I stop distinguishing varieties and spaces. So functor I disappears forever, and I don't make any difference between the two. The last remark, note that the property number 2, the fact that I computes with limits, imply in particular that I takes monomorphisms to monomorphisms. That's the thing which is good to know, because monomorphisms play a special role in the homotopy theory. So to say that something is a monomorphism of spaces, and that's not exactly true. Anything which is monomorphism of varieties is a monomorphism of spaces. So strictly speaking, a little bit more monomorphisms of spaces than varieties, but who cares? Fine. Okay, now we go to define to homotopy theory proper. There is only one non-trivial definition here, and this is the definition of weak equivalence. I'll give there are many equivalent ways to approach it, and as usually, one of them is convenient. I mean, one definition would be convenient for one type of computations, another one for another, and then half of the actually written stuff about the theory consists of proving that all the different definitions agree. But I'll just pick up one which appears to be most intuitively understandable, and I'll define weak equivalence, the class of weak equivalences, as the smallest class satisfying certain properties. So my weak equivalences will be defined in a very non-constructive way. I'll also formulate a theorem which roughly says that they can be formulated in a more constructive way. So let's see. We want to make things so we want to define the class of weak equivalences. So there is let's denote this class, which we're going to define, by WA1. So this is a class of morphisms in Yes? No. If you have semi-normalization, it goes into an isomorphism. So backwards map is not there. It is exactly localization by universal homeomorphisms, to be more precise. Excuse me, not all universal homeomorphisms. That's why I wasn't formulating it this way. It's a localization with respect to those universal homeomorphisms which induce bijections on the set of k points for all fields k. So for example, a purely inseparable extension is not going to become an isomorphism. I mean, so some like Frobenius is not going to become, geometrical Frobenius in characteristic P is not going to become an isomorphism in this approach. But semi-normalization is. But now this last statement was correct. It's exactly localization with respect to all universal homeomorphisms which give bijections on the set of k points for any field k. So it's the smallest class of morphisms such that. Now let's list all the natural properties one wants to have. Do you have more chalks? The first absolutely most fundamental property, of course, is this one. So the second property is that this should be a class of weak equivalences, so it should be the class of morphisms which go to isomorphisms after localization. So if f and g is a composable, well, maybe that's a hard way of saying it. So that's a standard thing. If the class is closed under compositions, and also if the composition of two morphisms is a weak equivalence, and one of them is a weak equivalence, and the third one is. Definitely true for any class of morphisms which is the class of morphisms becoming isomorphisms with respect to some functor. So the C condition is a tricky one, and it says the following. So let's consider, again, a co-Cartesian square maybe I shouldn't be doing this, sorry. So co-Cartesian is the same as push forward, is the same as, I don't know, what else? Co-fibered. So for any co-Cartesian square such that, let's take this to be f. Let's take this f. Such that I is a monomorphism and a one weak equivalence. Then I prime is an A1 weak equivalence. And C2 in the same situation, if the square is such that I is a monomorphism, and F is a weak equivalence, then G is a weak equivalence. Finally, the last one, let's place it here. The last property which we want is that what it's usually called, well, it usually says that the class of weak equivalences is closed under infinite compositions. So I'll formulate it this way. For any partially ordered set, in a diagram of spaces parametrized by I, such that the morphisms xi, xj are, let's again make them monomorphisms and weak equivalences. The morphism, again the morphisms from xi to the colimit of this diagram are weak equivalences. Pardon? Yes, I'll formulate in a second the theorem which will specify this. Yeah, I just wanted to make things simpler, and it's unnecessary. There is a functor. I mean, one can either consider simplicial spaces or just spaces, and one gets two different closed model categories, but with the same homotopy category, because since spaces is a co-complete category, and there is this canonical co-simplicial object there, which is formed by algebraic simplices. And using this, one can construct geometrical realization from simplicial spaces to spaces. Playing with this functor, one sees that one doesn't really need this simplicial dimension. It's important for proofs, but it's not necessary for definitions. Fine. So this is our definition of weak equivalences, which is, as I said, extraordinary non-constructive. So for all we know, all morphisms are weak equivalences. Yes?
So why did you include condition 2?
Why? Because it has to be included. I mean, because otherwise you don't get enough.
Where does it come from?
It comes, well, let me formulate a theorem, okay? And then I'll. Now here I'm formulating a theorem for those who know what closed model category is. For those who don't know, it doesn't really matter for what I'm going to say afterwards. So we introduced the class of weak equivalences. Now let me also introduce the class of cofibrations, which is defined to be just the class of all monomorphisms. So the class C of cofibration is the class of all monomorphisms. The class of A1 weak equivalences. Further denoted by FA1, the class which we call the class of A1 fibrations, and which is defined to be the class of morphisms having the right lifting property with respect to the intersection of these two classes. So, right lifting property. I said that the theorem is formulated for people who know the language of closed model categories just to make them happy. For those who don't know, it's completely irrelevant. For what I'm going to talk about, not for the big thing. I mean, it's an extremely important technical language, but not for what I'm going to say afterwards. Not directly. I'll reuse this space. Theorem. Classes C find a proper simplicial closed model structure on the category of spaces over T. Please don't. I mean, I have to specify exactly where the simplicial structure comes from. What I want to say with the theorem is that there exists a simplicial internal home object, basically. And I don't honestly remember exactly the definition of simplicial, but I know that it's true. So what the theorem says is that most of the standard intuition from the homotopy theory can be applied to this category as long as one replaces in one's mind the notion of, say, closed embedding by this cofibration, which is just monomorphism, notion of ordinary weak equivalence by A1 weak equivalence, and the notion of a fibration by this A1 fibration defined in this bad way. Yeah, well, there is actually one important example. Yeah, I'll talk about it in 2 minutes. There is one and only one example when it's tractable, and it's degenerated. So, no. Well, there is also some kind of a theory of quasi-fibrations, but we don't know much about it yet. So this definition of fibration is completely not geometrical. There are almost no fibrations of finite time. And it's only practically, I never used it. I mean, one always works with these two guys. And the fibrant side of the picture is still very much underdeveloped. Okay, everybody saw it? Okay, so here is the fundamental definition. So one defines this homotopy category as localization of the category of spaces with respect to A1 weak equivalences. Properly speaking, let me add here word CDH, which I refuse to explain. But it's sitting here. So one denotes this category by, I'll just denote it by H of K. Is it too low? Sorry. I'll denote it by H of K. The proper notation for this thing should be the following. This construction is a particular case of a general construction. And in terms of this general construction, this should be written like something like this. HA1 schemes K CDH. But we don't care. We look at this thing. Now, I'll mostly consider in the following lectures the stable homotopy category. So this is kind of introduction, which I wanted to give all the precise definitions so that I can define the stable case. So I'm not going to talk about unstable category almost. I mean, I'm not going to talk about it at all. I'll give now two examples of morphism sets in this category which can be computed. One example relates to this question about fibrations, and it's kind of trivial. And another example is more sophisticated, and I won't be able to give a proof. But the first one is so simple that one can actually see how it goes. Let's call it a lambda. So here is the fundamental, simplest possible example. Is it low? I can't. So let's consider X, which doesn't have any affine lines on it. So almost any X, basically, from the point of view of kind of standard intuition and algebraic geometry. So let's take such X that morphisms from Y cross A1 to X are the same as morphisms from Y to X. For example, let's take X to be any curve of genus greater than 0. Or let's take X to be a curve of genus 0, but minus, say, more than 1 point. So for any X like this, morphisms from Y to X in the homotopy category are exactly the same as morphisms from Y to X in the category of algebraic varieties. So if I restrict myself to the subcategory of varieties which don't have any affine spaces lying on them, then the functor from this subcategory to my homotopy category is a full embedding. Modulo this normal. I should have added normal variety. This also gives an example of a fibrant object. For any x like this, considered as a space, is a fibrant object in the sense of this closed model structure. Yes. Given any x like this is fibrant with respect to this closed model structure. So for any x like this, the morphism from x to spec k, canonical morphism to the point, is a fibration, belongs to this class. Fortunately not. No. No. This I don't quite know. I'm not sure. I mean, if one takes all other examples of fibrant objects I can think of are sort of infinite dimensional. But maybe there is some freak example of a gadget which is finite dimensional and still fibrant and doesn't have this property. No, characteristic 0 is completely unimportant so far in anything I was saying at all. At some point it will. Okay, I'll promise to do my best to try to mark this point explicitly when I start using it. So far it's irrelevant. Let me also mention that the reason I'm using this approach, there is another approach which actually works better in some sense in arbitrary characteristic, because it allows to go further without using resolution of singularities, not up to the very end, but further. And the reason I'm using this one is because I'm beginning to believe that there is a way to go around and use this approach without knowing resolution of singularities. So that's why for about a year and a half, I didn't like this approach because I didn't think that it's going to work. Now I'm beginning to like it again. So that's one example. In the proof of this lemma, everyone should be able to reproduce it from what I said. It really doesn't require anything. Now the second example, let me call it proposition as being more sophisticated one, requires a little bit, requires more effort. Okay, let's be very fast and do this. So let's take an algebraic group G. Let's take just finite group G for now. Let's take a finite group G, a finite group, and I'll assume that at this point that the characteristic doesn't divide the order of the group. So this is going to be important. Now I'm going to define something which will be called geometrical classifying space for the group. I'll be skipping all the details whatsoever because I just want to give an example. Something I'm going to call BGM G rho. Now rho is a representation, a faithful representation of my group G over K. I choose a faithful representation, and then the result is not going to depend on this representation up to a canonical A1 weak equivalence, but one needs representation to start with. So this gadget is obtained as follows. So So let's denote by U the open. So here is representation that V is a vector space over our field K. So let's denote by A of V the corresponding affine space. It's basically the same vector space. It's just considered as an algebraic variety, nothing else. Then this representation defines an action in the obvious categorical sense of this finite group on this affine space. Now, this action is not going to be free. It's going to have all kinds of points with non-trivial stabilizers, like 0, for example. And let U be the complement to all those points. So U is the maximal open subset on which G acts freely. That's in fact denoted by U1. Now for any n, I can consider the direct sum of this representation with itself n times. Going to be going in here defines me an action of G on the affine space of this thing, which is the affine space of V times n. And I may consider Un the subset where G acts freely in this bigger representation. One can look and observe that the codimension of the complement is going to infinity as n grows. So the complement gets sort of smaller and smaller. Also, we have closed well, we have maps at least from un minus 1 to un, which just correspond to some trivial embedding from Vn to Vn plus 1. So one coordinate is 0. So I can take the quotients, and these are free actions of a finite group on a very smooth, very nice variety. So the quotients are some smooth varieties. I define my BGM of G to be the co-limit, direct limit of this quotient. Now the quotients themselves are smooth algebraic varieties of finite type, but of course the co-limit is not, but it's perfectly well defined as a space. So one proves two facts. Fact number one is that for any two faithful representations, these guys are A1 weakly equivalent, canonically A1 weakly equivalent. And the second thing is this. Turns out we can compute morphisms with values in this object, and they look as follows. So for any x, can everybody see, or is it? So for any x, the set of morphisms with values in this geometrical classifying space of G is just H1 in the étale topology of x with coefficients in G.
So if I take the direct limit of the un and map over that, just like a function.
That's a very good question. That's a bit tricky. So thanks. I wanted to mention it, by the way. It's very important where we take the quotient. As I mentioned, this functor I, which I threw out of my notations, commutes with some coproduct, with some colimits, but not with others. Quotient with respect to a finite group action is an example of a colimit to which this functor doesn't commute. So taking quotient in the category of algebraic varieties and considering the corresponding space is not the same as taking the space and taking the colimit, the categorical quotient in the category of spaces. That's a crucial point which introduces almost all the complications into the theory. This one is the quotient in the category of varieties. So one takes the actual algebraic variety and considers it as a space. What we should actually do in order to distinguish these guys, let's call this quotient geometrical quotients. Now let me remark that one can do exactly the same thing, of course, taking instead of geometrical quotient, taking naive quotients, so the quotients in the sense of this category. And then one gets another object which is called simplicial classifying space of G. And then morphisms with values in this object are going to be CDH cohomology with coefficient in G, which are sort of closer to the risky than to a tau. Okay, that's it.
Is the UN sort of contractible, so like getting larger and larger?
Yes, yes. So I actually didn't answer the question about the fibration. So first of all, this limit, if I look this UNs and go to the infinity, I take this U infinity as a space. This space is contractible. That's the first thing. The second thing, the projection from this space to this BGMG is a fibration, actually. The thing is, this map is not an epimorphism of pi naught in appropriately defined sense. So even though it's a fibration, it doesn't say much, because there are so many connected components down there which completely don't come from up here that it doesn't help.
Now can I ask you what's CDH?
Yes. So CDH topology is the topology generated by the following two types of coverings. For any square of this form, the map from the disjoint union of Z and XZ to X is a covering. And for any square of this form, the map from the disjoint union of U and V to X is a covering. So the smallest Grothendieck topology generated by these two types of coverings is called CDH topology. And the letters come from completely decomposable H topology, and H topology originally was coming from homotopy, so it has nothing to do with homotopy.
How does it relate to the topology of
Yeah, if you forget these guys, you see there are two types of squares. If you forget about smooth varieties for 1 second, okay? And let's consider all varieties. If I take the topology, Grothendieck topology generated by these squares, I get exactly the Nisnevich topology. If I mix these two together, what one gets is called CDH.
So which one's okay, so the other homotopy category is different?
What happens? Okay, what happens is the following: that taking CDH topology on all schemes gives the same answer, at least stably, as taking Nisnevich topology on smooth schemes. But in fact, the accurate statement is that it's only true. One needs resolution of singularities. So far, I believe that it's actually unnecessary, and the statement is only valid stably. So unstable categories, strictly speaking, are slightly different, and this is an unpleasant point, which.
So also you're taking a finite group, but you algebraic group will work.
It depends what kind of algebraic group one takes. I'll discuss it next lecture, but essentially in a stable setting. But basically, if one takes, say, GLN, well, if one takes, say, GL infinity, one gets algebraic case here in some sense. But the point is that this cannot hold for an arbitrary G because the function on the right-hand side is not homotopy invariant for an arbitrary G. So if it were, then it would have been correct.
Does it make sense for X space? You just define it's all homological spaces usually.
Yeah, just as the same thing.